So, good morning. Welcome, Professor Narayanan, distinguished guests, esteemed cement professionals, scientists, engineers, researchers, academicians, students, and friends from the innovation fraternity. A very good morning to all of you. So, Professor Narayan, I think we are audible.
Yes.
Yes. Okay. Thank you. It's an absolute privilege to welcome you today as we celebrate National Science Day, a day dedicated to the spirit of inquiry, discovery, and the transformative power of science. Today, we also mark a significant milestone with the launch of NCB Distinguished Lecture Series featuring renowned experts in the field of cement, concrete, and building materials, a platform that promises to inspire, educate, and push the boundaries of knowledge in the critical domains. National Science Day reminds us the remarkable contribution of science of society, honoring the discovery of Raman effect by Sir C.V. Ramanji on this very day in 1928, a breakthrough that continues to resonate the scientific world. In that same spirit of innovation and progress, we gather here to explore how science can address some of the pressing challenges of our time, like sustainability, climate change, and efficient use of resources in cement sector. Today, we are honored to kick off NCB Distinguished Lecture Series with an inaugural lecture titled Novel Approaches in Cement Production, Coupling Materials, Efficiency and Manufacturing Approaches and Decarbonization. The cement and concrete industry, the foundation of modern infrastructure, is at a crossroad. It supports our cities, roads, and homes, yet it accounts approximately 7% of anthropogenic carbon emissions globally, and it is considered as one of hard to abate sector due to the process emissions from calcination of limestone. And the question before us is how to reconcile this paradox. How do we innovate to make cement production more green and sustainable while maintaining its strength, scalability, and affordability? Dear friends, our speaker today is uniquely equipped to enlighten us through the complex landscape. It is indeed my privilege to introduce the luminary who will deliver this inaugural lecture, Professor Narayanan Nethalia. Professor Narayanan is a full-time professor of structural materials in the School of Sustainable Engineering and Built Environment at Arizona State University, USA, with a PhD from Purdue University earned in 2004, where he focused on novel cementitious materials for infrastructure. He has since carved out an extraordinary career dedicated to advancing sustainable construction materials. His work spans the development of new cements and concretes, innovative structural systems, and cutting-edge manufacturing techniques like 3D printing of concrete, with all an eye toward mitigating the climate change. Professor Narayanan has authored over 200 research papers in referred journals, sharing his insight with the global scientific community. His expertise has taken him across the world, delivering keynote addresses at prestigious conferencing and advising startup companies in the novel materials space. Beyond academia, he is deeply engaged with industry, consulting for firms in green energy, materials, infrastructure, and construction. His accolades speak volumes. A fellow of American Concrete Institute and recipient of coveted Walter L. Hoover Civil Engineering Research Prize from ASCE. These are just to name a few. What makes Professor Narayanan's work so compelling is his ability to bridge theory and practice, science and application. His lecture today will dive into novel approaches that promises to revolutionize cement production, strategies that optimize material efficiency, rethink manufacturing processes, and significantly reduce carbon footprints. As we launch the NCB Distinguished Lecture Series, with this inaugural lecture, we set the tone for what will come in future, a platform where ideas will flourish, where experts will challenge us to think differently, and where solutions to the global challenges will take the shape. So without further ado, please join me in extending a warm welcome to Professor Narayan, and I request Professor Narayan to share his thoughts, please. Welcome, Professor Narayan.
Thank you. Thank you very much, Dr. Singh. I'm audible, right?
Yes, so please share.
Yeah, let me
share your PPT.
Yes, let me share my screen. Is it visible now?
Yeah, your screen is visible. Please share your presentation.
Is it now good?
Yes, but it's not in presentation mode.
Okay, okay. Let me see.
Now it's fine. Now it's fine.
Okay,
It
okay.
was
Now it's fine, right?
Please share. Please share again. Please share again.
Okay. How about now?
Yes, fine.
Fine. Wonderful. Thank you very much, Dr. Singh and NCBM for giving me this opportunity. It's indeed a pleasure to be here talking about novel approaches in cement production to a whole gamut of people who are dealing with cements every day. And there is nothing that is more exciting than being able to share some of what we have learned and to learn more from all of you about the advances in this field. So let me get into the crux of the problem. All of you know this, that we are in a period of climate change.
Professor Narayan, your video is off. If you have you deliberately kept it off, otherwise
No, because let me do it. Let me do it. When I shared it, it probably was off. Now I'm visible, right?
Yes.
Let me share the screen now. Entire screen, share, and good now?
Yes. Okay.
Okay, wonderful. So the whole idea of global climate change, we are all dealing with it. There are varying levels at which people believe this, but generally it is well understood that anthropogenic carbon emissions are contributing to climate change, contributing to a lot of effects in global climate. So um, how close are we to 1.5 degrees Celsius rise that Paris Accord wants us to be limited? We are not very close. We actually have gotten very close in 2024 to that 1.5 degrees Celsius. So we are in a place where we are already there. In current policies, if you do what we are doing now, we are ending up with 2.5 plus degrees Celsius by 2100. If to get to 1.5, we have to do a major carbon budget reduction, and we have to use all possible levers. And why are we so worried about it? Construction industry is one of those major industries that contribute significantly to climate change. Not just cement and concrete. We talk a lot about cement and concrete, but lots of other construction materials also have a very deep carbon impact. If you look at building sectors, about 90% of emissions come from building materials and about 10% from building operations. So the operational energy, where you look at HVACs, where you look at lighting, you look at all of that, is only about 10% the global scheme of things. 90% comes from embodied carbon because of materials. And if you look at the figure below, concrete has a much lower carbon impact per ton or per unit volume of material. But then the amount of concrete that we use is tremendous. It is a material that is used in quantities second only to water. So we have extremely high use of cement and concrete, which will give you an extremely high carbon impact for for that. Let me get my pointer here. For cement and concrete. So you have, even though the embodied energy is low, the embodied carbon for cement is pretty high, and we need to control that. All right. So cement production, again, I'm preaching to the choir here. Everybody is an expert in this. You have a raw materials preparation stage where you excavate limestone, you crush it, you proportion it. The raw meal is ground, it's homogenized. Pyroprocessing stage, you have pre-calciners, and then it goes to a rotary kiln. The kiln gives you the clinker as the output. The clinker is taken down, ground with gypsum, fly ash if you're doing a blended cement, put in silos, transported. So all of these, again, extremely complicated operation to give you a material that is fairly cheap, even though we complain about the cost of cement. For the kind of operation that it undergoes, you're eventually getting a fairly cheap material at the end of the day. And as cement companies, most of you would know that you are in the business of selling it by volumes, um, not by value per unit margin. So it's a pretty complex process. Now, if you look at the first stage, right, that's where all the raw materials are. And what's our raw material? It's limestone, calcium carbonate. Every cement company in the world uses limestone or calcium carbonate, which in the pyroprocessing stage, in stage 2, gives you directly the fact that CO2 has to be emitted. If calcium carbonate has to be treated and you have to get lime to make it into your C3S and C2S and C3 and all of that, you have to get the carbonates out, CO2 out. So pyroprocessing is effectively to get your CO2 out. That is your process emission. So two things, pyroprocessing or heat treatment will get you your CO2 out. That CO2 is emitted, and then the pyroprocessing, to get to 1500 degrees Celsius in the kiln, you are using fossil fuels which have their own embodied carbon impact. So both of these things together will give you the major impact of CO2 with respect to cement production. So one thing is very clear: limestone as a raw material has a CO2 source. You really have to go away from limestone if you have to do half the embodied carbon reduction. And the remaining is by changing the fuels, changing the processes. So in stage 1 and stage 2, you have quite a bit of targets to control your carbon emissions. Again, how much do we do it? About 50% from your calcination process, that's your process emission, about 35 to 40%, depending on where you are, what kind of processes you use, is your fuels for the high process heat. And that's where most of your emissions are coming from. And of course, there is a little bit of grinding, little bit of transportation, all of that. But we'll focus on the two major components, which is the calcination component and the process heat component. Now, traditionally, if you look at global cement production, you typically talk about this number Dr. Singh alluded to when he made his opening remarks about the 7% carbon emissions by the total amount of carbon emitted from cement. Iron and steel is 8%. You mix iron, cement, and steel. Again, reinforced concrete structures need steel all the time. That's about 15% of emissions. Again, steel is used in lots of different applications, but about 15% of emissions in the buildings and infrastructure sector. But the picture on the right is even more telling. In terms of most emissions per revenue dollar, kilogram of carbon dioxide per dollar of revenue. And that's what I was telling. This is a low cost, low margin industry that rely on heavy volumes. You look at that in terms of per kilograms of carbon dioxide per dollar, because the dollar is so low, because the value, the price is so low, the kilograms of CO2 per dollar is so high. Look at that margin, 6.9 kilograms of carbon dioxide per revenue dollar. And that is where economists are really worried about the cement sector, right? Because when you combine the carbon emissions and the associated revenue, you have a much higher impact than pretty much every other industry. Even oil and gas, iron and steel, mining, everything else pales in comparison with the impact that cement makes with respect to revenue generation. Why is revenue generation important? Only if you have revenue generation or very high revenue generation from a certain industry can you motivate governments and motivate investors to invest more on mitigation technologies, right? You have an industry that's giving you a very high revenue, you are much more driven to do mitigation measures. Whereas in our industry, the dollars are low, the revenue is low, mitigation also lags behind. And that's why we always talk about cement industry not catching up with how lots of other industries are doing decarbonization. Not because of lack of interest, not because of lack of technology, not because of lack of processes, but just because the economics is not driving it the right direction. If you look at cement emissions, in 2023, we're about 4.1 billion tons of emissions, of carbon emissions, 9% coming from India alone, 16.1% from Asia, that's excluding China, Japan, and India. United States about 2.3%, because again, out of the 4 billion tons of cement that's manufactured in the world, United States make only about 100 million tons. So it's a very, very small fraction. But if you look at Asia and China, and Asia minus China, India, and Japan, and the remaining Asian countries, you see this very, very big band of emissions coming out from this part of the world. So again, emissions knows no boundaries, which means emissions anywhere is the same as emissions everywhere else in the world. So that's why we have to be very careful about it. Across the value chain, construction accounts for about 25% of global greenhouse gas emissions across the value chain. So if you look at the overall value chain, you have about 25% of global emissions from construction ecosystem alone. All of this puts us into a place where we need to really think about how we deal with cement and concrete. Again, re-emphasizing the idea that in construction, cement manufacturing accounts for the most emissions. About 75% is coming from complete cement manufacturing. Concrete production, construction, use, end of life are fairly small contributions to the overall emissions. Again, focusing on why we need to innovate cement manufacturing. Here is what U.S. Department of Energy came out with in what they call their early liftoff practices. So again, same ideas: raw material extraction and quarrying, clinker manufacturing, cement production, cement retail, concrete production, construction, end users. Again, this is a U.S. scenario. So roads, highways, and bridges account for about 25%. Infrastructure maintenance for about 7%. Buildings account for about 55%. Most of concrete use is here. And then if you look at decarbonization potential, this is from an Indian scenario. How do we decarbonize cement production? If you change fuels, biomass, tide-derived waste, hydrogen, 25% of emission reductions. If you use clinker substitution, all of you are very familiar with this. India is perhaps fairly advanced in clinker substitution ideas. You're looking at 42% reductions carbon emissions by 2050. In the US, we have a problem here because we don't have good fly ash. The power plants are being phased out. We don't have good coal-fired power plants, many more of good coal-fired power plants, which means they're being phased out. We are having a paucity of fly ash, which means we have to rely more on natural parslans, reclaimed, harvested fly ashes, etc. India yet doesn't have that problem. If you look at kiln efficiency improvements, about 12% of CO2 reductions. And then synergistic effect of a lot of other decarbonization measures, so about 75% reduction by 2050. So what are the mitigation pathways? You look at here, the process emissions, more than 50%. Thermal emissions, because of the fuel, 40%, and then everything else, cooling, grinding, mixing, about 10%. How do we control the process emissions? One way is to use less clinker, use a lot of SEMs. The next way is to use a source of lime other than carbonates. Can we use calcium silicate? Is that possible? We have lots of calcium silicate. The process gets different, but again, limestone is so much more abundant. Every cement plant in the world currently is designed to process limestone, so that and it's situated right next to a limestone source, so that becomes a problem. Carbon capture and utilization is a good technology. I will not talk about carbon capture and utilization in this lecture. It's a completely different lecture requiring us to think about processes very, very differently. And I don't want to mix too many things, so we won't talk about carbon capture. But there is electrolysis-based processes that can process limestone to lime without emitting CO2, and I will talk about a few of those. which is probably the only way where we can use a limestone source and still get CO2 free lime. And then with thermal emissions, what are the pathways? Alternate process heat. Can we use electricity, for example, instead of coal fired? Can electricity provide high temperatures? Alternate manufacturing schema. Can you look at other ways in which we can manufacture? Renewable fuels, energy efficiency improvements. Every cement company is doing it. We are probably at thermodynamic limits of energy efficiency. Most new cement plants, most good cement plants are operating at thermodynamic limits of energy efficiency. There is really not much more of energy efficiency possible, meaning that we may have to look at these methods. So combination of this is what we should be looking at in terms of mitigation pathways. Again, another way to look at it from a net zero roadmap, you have carbon capture, utilization, and storage being a very big chunk of that by some accounts. Again, this also can be removed if non-carbon based processes to get lime from limestone can be developed. So this is, if you're using the current processes, CCUS will have a big role to play. If you're using other formulations, other types of lime generation, this becomes a little less important idea. Impact of mitigation measures. Again, you talk to everybody, they'll talk about these four things. Energy efficiency. If you go to 2050 scenario with energy efficiency, you can make a dent of about zero point 0.2 degrees Celsius to get to 1.5. If you're 2.9 at 2050 now, zero point 0.2, very low. Alternative fuels, you get lower. Clinker substitutes, which we do quite a lot of it. We are doing clinker factor in many cements are in the global average is about 80 or 85, but in a lot of countries, the clinker factor has gone down to 0.6 to 0.7. So it's still it's at a very high level. And then they club everything else into these new technologies. And this is where we have to focus quite a lot. And then, of course, alternate building materials, other approaches, changes in design. If you deal with reinforced concrete, you know that we don't design reinforced concrete structures well enough. We do lots of redundancy. We do lots of over design. We put in a lot of concrete in places where we don't want concrete. That's where technologies like 3D printing comes in, which again is a completely different topic, but all of them will add to making our sector more sustainable. Again, we are focusing on cement manufacturing alone now, so I will not get into a lot of other topics like 3D printing or even technologies like amine scrubbing and all for CCUS. We'll just focus on a few direct reduction technologies. All right. This is again DOE's four-track pathway to liftoff. They broke it down into currently deployable measures. What can we currently deploy immediately? Clinker substitution. We can extend it. We can stretch it. Energy efficiency. We can do that. We are doing it already. Alternate fuels. There is natural gas instead of coal, even though natural gas also has carbon impacts, slightly lower than coal. Can we do that? And all of those, if you do the lift off, you need about $5 to $10 billion of capital. The abatement potential is 30 to 40% of the existing CO2 productions. And then they couple the next two very big technologies, CCUS and alternate production methods. The reason why they clubbed both is that CCUS is an important lever if you are relying on the existing production methods. But if you're using alternative production methods, then CCUS is not something that you may want to put in. Like I said, electrolysis may not have any carbon emission at all, so there is no point in capturing and storing it. But if you do that, if you combine that, look at that scale, 5 to 10 billion for clinker substitution, energy efficiency, etc., you're looking at $100 billion to scale up these two technologies. The abatement potential is pretty large. And then alternate binder chemistries. This is something that we know for quite a long time. Geopolymers have been there for a long time. Calcium sulfur aluminate cements have been there. Balytic cements have been there. Magnesium-based cements have been there. They have not been adopted by the industry in any significant amounts because we are so happy with Portland cement. We know exactly what ordinary Portland cement does. We have so much of confidence in the system. We know what it is. Alternate binder chemistries have really not picked up well. Can it pick up well? Yeah, it might pick up well, but will we be able to produce 30 billion tons of concrete with alternate binder chemistries? Very unlikely. So there is a lift-off potential, but the lift-off potential is not nearly anywhere close to what we have with traditional Portland cement. And everybody accepts that. They don't even put in any dollar figure nor an abatement potential because the details are less clear. We don't know what the takeoff is. So we'll focus on the first three methods, currently deployable measures and alternate production methods. Like I said, I will just ignore CCUS for the time being. So we'll talk about A and C in the remainder of this lecture. So near-term decarbonization pathways, manufacturing can be made better. Concrete mixes can be made much more streamlined. We make ultra-high performance concretes with 150 megapascal strength now, with high cement contents, but the overall volumes of concrete are much lower. Can we make design much more efficient? Can we put in concrete only where that's needed? Can we make thinner sections? Can we design better? Can we reduce reinforcement? Lots of other ideas to do. And design of structural systems, service life elongation, all of those will end up with reduced demand. So scope of emissions, 60% from materials, 40% from energy, capture overall about 80%. We will, again, these are all based on what different technologies offer. Again, for example, material efficiency from SEMs, binder efficiency, alternate lime sources, like I said, calcium silicates, magnesium-based cements, etc. Energy, new generation process controls, electrification, which we talk about quite a bit because that's one of the core areas of research that we are very deeply engaged in now, in terms of electrification of processes. And then, of course, capture, which I said we will not cover now. Supply demand side strategies, again, something to be very, very cognizant of. If we want to get to net negative emissions by 2050, we're not going to happen. India has a 2070 target. US had a 2040 target, but with the current change in administration and changes in the priorities and the way in which monies are allocated, I don't think 2040 or 2050 is a realistic goal. So we don't know where we are going to go with. But if we want to get there, we have supply side strategies. That's all the blue strategies right there. The best supply side strategies still will get to only, this much. Then you have to have emerging supply side strategies, CCUS with concrete curing, low carbon chemistries, and then demand side strategies where material design, waste reduction, end of life options. Again, simply all levers have to be used concurrently. We can't just say that we will use one lever and get to a net negative or close to net negative emission. Whether it's India or China or the US or Europe, any country, we need to have a combination of supply and demand side strategies. Materials efficiency, and here is where I'll pick up with a few things from a materials efficiency point of view. Here is your OPC, 95% of clinker, 5% of ground limestone typically, or anything else that you have, gypsum. Portland limestone cements are becoming very, very common in the United States now. We have most of the cement companies converting them into PLCs, where you have about 15% of limestone, ground limestone in the cement, reducing embodied carbon by 10 to 15%. Incremental value for a 1.5 million tons per annum cement plant is about $9 million per year. Blended cement with fly ash, you have about 30% of fly ash that's blended. With steel slag, you have about 45% of that. LC3 getting popular. There's lots of push towards LC3 in the US, but with respect to clays and the ability to get the right amount of clays and the right type of the clays, pyroprocessing of clays, the energy required to calcine those clays, there are challenges, but you get about 40% of carbon reduction. Blended cement with natural pozzolan is a big thing, where lots of natural pozzolan resources are being identified. That's about 32%. So you get to about incremental value for a 1.5 million cement plant, because you're making less of clinker and more of the other things, you can increase your value. So that's your materials efficiency strategy. What happens with clinker supplements? The outlook for clinker supplements: alternate binders, new and innovative SEMs and fillers. 2020 to 2030, people don't expect any change. We are in 2025 already, but by 2040 to 2050, alternate binders are projected to go up. new SEMs and fillers. There are companies in the US, startup companies that are manufacturing new types of SEMs. Several new companies, which I very closely work with, are manufacturing new types of SEMs, low carbon SEMs for use in concrete. So that market has a very significant growth potential. Natural SEMs and fillers probably will grow for some time and then come down. Traditional SEMs in the US is going to come down significantly, so there's going to be a phasing out of that. Green clinker, there are green clinker plants that are coming out again, like I talked about, electrochemistry, for example, is another growing area. So we'll focus on the first and the fourth topics as we go through: alternate binders and green clinker, and how to make green clinker. Global SCM scenario, again, all of you would have seen these kinds of pictures: calcium, alumina, silica. Silica fume lies right here. Your Portland cement is calcium rich, and then all your fly ashes are somewhere here. And you can now, there's lots of these materials that fall in this ternary diagram that people use for a lot of different applications. There are even biomasses that people are using. Recycled glass is becoming very popular in the US. There are companies that are actually making glass pozzolans from recycled beer bottles and other glass waste sources. Limestone filler is very common now. 20-30% of limestone filler even sometimes is fine. Blast furnace slag, of course, it's a common material. So this is where the global SCM scenario is. Some of them well established, some of them working on it. Limestone cements, I talked about it. ASTM C595 allows up to about 15% of limestone in cements. What limestone does, again, most of you would know this, a small amount of limestone reacts with the aluminates to form what's called monocarboaluminate, and then a lot of limestone serves as filler. So there is a filler effect because of dilution. There's a little bit of a reaction effect. Eventually, at some dosage levels, you get beneficial properties and they come down. But again, filler effect is a fairly well documented phenomena. Porosity comes down, strength goes up at reasonably smaller replacement levels, up to about 5%, but people use even up to 15%. And especially if you have an alumina that goes along with it, you will have eventually more amount of reaction products. Synergy with aluminates, that's where all your LC3 come in. So if you do only metakaolin replacement, a calcined clay replacement, you get monocarbonates and hemicarboaluminates. Metakaolin plus limestone, you get a lot more of monocarboaluminates. And that's where you get the benefits with LC3 cements. But again, calcining clay is also an energy-intensive process. Getting clay, because most of your clay is coming from fertile agricultural land. So you don't want to be using agricultural lands to get your clay. That's another point. LC3 systems, most of you are very familiar with it. India is in the lead in developing LC3 systems. US is fairly behind now, but we are catching up with lots of new plans. Department of Energy funding, of course, we don't know with the new scenario how much of that funding will be realized, but Department of Energy was, until end of 2024, very keen on LC3 systems. Carbonatable cements, a great idea where you can take CO2 and start to carbonate. And there are several companies in this sphere. If you know Carbon Cure, Carbon Build, Carbon Limit, several companies, several startup companies doing a lot of different things with carbonating binders. Very easy to do in a when I say easy, relatively easy to do in a precast setup. If you have a CO2 source, there are companies that will simply take a flue gas. For example, you have a CO2 emitter, the flue gas, you take it directly and co-locate it with a flue gas source, and then carbonate your materials, and then make structures, concrete blocks, precast members, all of that. Very common approach to do to make that. Carbonatable cements are important. Fly ash can be carbonated. For example, if you have a calcium-rich fly ash, calcium hydroxide is one of those materials with an extremely high carbonation potential. For example, 1 gram of calcium hydroxide can theoretically absorb 0.5 grams of CO2, roughly. Right, so you have 50% of CO2 absorption capability for calcium hydroxide. When you have a Ca-rich fly ash, a class C fly ash, for which there's lots of free lime, and if you can activate that free lime, mobilize it, get to calcium hydroxide, lots of them are going to convert into calcium carbonates. And then add to that a little bit of pozzolanic and cementitious reaction, you get up to 35 megapascal strength without too much of a problem, even with a flue gas with 10 or 15% CO2. And that is a big deal if you can industrially and beneficially utilize it. Carbonate crystals growing around fly ashes, as you can see here. So that's another way in which, I mean, there's lots of research, lots of companies doing, not lots, a few companies doing this, making cement-free binders simply using carbonation. 35 megapascal is the high end of strength, but mostly for concrete block applications, you need 10 megapascal, 15 megapascal, easily attainable in that scenario. Again, this is how it does. Again, it's a very close relationship between exposure time, relative humidity, calcium content, all of that. But what happens with pure Portlandite? Like I said, final conversion, very high conversion, calcium rich and calcium poor fly ash, low amounts of conversion, but still enough conversion to get you to a good amount of reaction product formation. And the idea now, again, I'm going a little ahead now to tell you that if you want calcium hydroxide, you can have carbon-free production from limestone using electrolytic approaches. So you can create calcium hydroxide from limestone, calcium oxide or calcium hydroxide from limestone without CO2 release, which can then go into cement manufacturing, which means here is one way where process emissions could completely be avoided. And I'll show some of the methods. Scalability, economics, all are questions that we need to solve. Ultra high performance concrete again is a very good lever in this whole process as to how we can develop materials with extreme efficiency. Look at 175 megapascal strength with fibers, a lot of ductility also built into the system. You can really get concretes to do a lot of good things. Very high durability. You can see very low rapid chloride permeability, very low migration. So these are materials with extremely high durability. And if you look at strength per CO2 equivalent or flexural strength per CO2 equivalent, they are much, much, much better than Portland cement or regular OPC concretes. And here is a UHPC mix that gives you 150 megapascal strength with 50% cement replacement. You have 14 times the strength per unit carbon emissions. And these are advantages that we can make use of. You can make thin members. India, again, is pretty ahead in UHPCs with lots of bridges that are being built in UHPC with UHPCs in several parts of the country. So again, another way in which concretes can be made in a sustainable fashion. But let's get back to cements. What are the low carbon alternate manufacturing approaches? So far I talked about materials efficiency. How do we use Portland limestone cements? How do we use LC3 cements? How do we use UHPCs? What are the overall impacts of that? What is carbonatable cements and all of that? Now, how do we make OPCs in a low carbon method? Right? So again, like I said, energy and process efficiency in existing manufacturing facilities, you can definitely do that. And we are very close to it. Thermodynamic limits are already there. Can you add new energy efficient sub-processes, including CCUS? You can absolutely do that. But two things we will focus are on kiln electrification and on electrochemical processes. Kiln electrification is simply the idea that you replace your fossil fuel with an electrified source of energy. There are, as examples, vertical calciners, Lilac, rotodynamic heating Coolbrook, which is actually working with a few Indian companies in doing it, and then plasma electric arc furnaces. Again, there are a lot more technologies, but we'll just focus on calciners and plasma or arc furnaces. And then there's a bunch of electrochemical processes, sublime systems, brimstone, Chemen, ZeroCal. These are all electrochemical processes. But note, all electrochemical processes only produce lime or calcium hydroxide. You have to still combine it with silica and alumina to form cement. That will require further energy, but then that can be done through electrification, which is again from renewables, which means you combine electrochemical processes with kiln electrification. Basically, add these two. That is probably the most efficient, futuristic way to manufacture zero carbon cement. Again, remember, I'm talking about a scenario where you don't have to use CCUS. Right now, with an existing facility, CCUS becomes an important lever, but in a futuristic scenario, 5, 10 years down the line, the combination of these two technologies, where you can have electrification plus electrochemistry, provided that, again, this is fairly well scalable. The scalability of this, people are working on it. There is a company, for example, Sublime Systems is putting up, I think, a 100,000 ton plant in the, or 50,000 ton plant in the United States as we speak in Massachusetts. So it is scalable. There are phases in which how efficient, how economical, questions need to ask. So talking about these alternate technologies, if you look at different ways. So direct combustion, direct processes, electricity production. And because electricity can be obtained from renewables, solar, wind, hydro, nuclear, all of that, this can be produced. We are talking about systems that are heavily electricity dominant. So electrified calcinations and electrochemical processes, like I said earlier. Renewable electricity and process it again, United States scenario, we are looking at by 2050 about 44% renewables. Coal is going down from a very high number to about 10% by 2050. Nuclear will be about 12%, going down or fairly constant because of all the issues with or concerns about nuclear plant. But the current US administration apparently is heavily nuclear favoring. So we'll see what happens with that. But renewables anyway will go up to about 44%. Out of that, 51% solar, 31% wind, geothermal, hydroelectric, all of those are small numbers. So again, this is US scenario. India could be different. But the idea that you have a lot of solar energy and wind energy that could be harnessed, and if you can heat storage technologies, this becomes a very viable approach. Again, here is a schematic of a renewable energy system. National Renewable Energy Technologies Laboratory is doing a lot of those work where they are taking renewable electricity, having heat storages, and then giving it through power cycles to get electric heat. There are companies that are taking electricity out of all these renewables, storing it in heat storage batteries, and going through several power cycles to put in as heat storage heat for high heat applications. They're able to deliver 1200 to 1500 degrees Celsius of heat with this. So again, technologies are improving where you can use these renewable electricity as process heat. So kiln electrification challenges the ability to provide high temperatures for that. So which means we need to really look at heat transfer mechanisms. Again, this is really, really fertile research area right now as to how to do this. Can we use waste heat from calcination of limestone to calcine something like clays so that this unique process produces both calcined clay and lime? The lime will go to your cement process. Calcined clay will go to the final grinding process where you can produce an LC3 cement, for example. The advantage of this is that with pure limestone, not mixed with silica sources, not mixed with alumina sources, will give you an almost pure source of CO2, which can be captured and diverted somewhere else. So again, augmentation with carbon capture is possible if you do stage electrification. So here is a schematic of how an electrified heat calciner will work. Raw meal will come in. Again, when I say raw meal, I really mean here only the limestone, right? Because we are only calcining it. And then when you go to rotary kiln, you can do the limestone and you can inject the other materials also. So basically, kiln is the only one that requires the high heat. The kiln can be shorter if you are doing it. And then if you have a CCUS method where you can get CO2 from calcination, then if you need co-location of a facility that uses CO2, you can make chemicals as well. So the future cement companies, again, this is a really futuristic thinking, out loud thinking scenario. A future cement manufacturing process, a facility will have, if it is CCUS integrated, will have something else that also a value added material that's also being produced, chemicals or hydrocarbon or whatever that will be produced, or plastics that will be produced. Electrified systems can be modular. You can have a lime plant and then combine it again. It doesn't have to be wet grinding, but lime plant can be combined with a cement manufacturing plant to get a different cement. So electrification could also be modularized. So an existing facility, take the pre-calciner alone, calcine everything in the pre-calciner part, and then do the kiln later on. Modularization possible. Fluidized bed reactors are becoming common. They are very, very efficient in terms of heat transfer. Remember, at the end of the day, what we want is to have all these particles, which are a few microns in size, going into the calciner. So you have to have very high heat transfer efficiency, both or through conduction, convection, and radiation mechanisms. You have to really drive all of those. Here, what happens is raw meal particles are suspended in upward flowing gas, which means very effective convective mass transfer. The problem is that fine raw meal sometimes are poorly fluidized. You may have to mix it with other particles and stuff like that. But such a design, the vertical calcining, vertical fluidized bed reactors, for example, Lilac does vertical calciner, where the material flows down and calcines as it flows down in a gas environment, which is a very good way of doing it. Induction heating, people are trying very hard to use magnetic induction. This is a very energy efficient process by providing volumetric heat rather than through individual conduction mechanisms. Scaling efficiency is a challenge, but there's lots of work going on in the inductive heating area. We have a small facility that we are building that can do about 20 pounds or 10 kilograms an hour of cement with inductive heating. There are challenges with respect to how you directly provide the heat, but efficient process means that your overall energy efficiency is going to be much higher. This is another very interesting technology that is being investigated. Europe already has a pilot plasma plant, and plasma, you can use any inert gas, argon, nitrogen, etc., to produce plasma, but you can also use CO2 to produce plasma. So if you calcine your limestone independently, the CO2 that comes out of the calcination can be used as a plasma carrier, plasma gas, and then a plasma torch can heat the raw meal to very high temperatures. The process is instantaneous, but again, heat transfer, control of the amount of heat, melting of different phases, all of those are challenges. But this allows you to do a very nice retrofit strategy. So if you have a calciner that simply calcines, and then all you need is a rotary kiln, the existing kiln, instead of your burner or your energy source in the kiln, you simply have to augment it with a plasma generator, which means if the plasma is coming from green electricity, your entire heat emission CO2 is taken care of. If the calciner is doing pure limestone, that CO2 can be captured. Waste heat recovery or CO2 can be directly given back to the plasma generator. You can use the CO2 as well. So lots of benefits to such a technology. We are doing a pilot plant to actually look at this process. Again, 10 to 20 kilograms an hour plan to see if this is a really scalable process. Lots of challenges with respect to heat transfer and things like that. But we think this is a viable option where you can eventually deal with a low carbon cement at the end of the day. Self-propagating high temperature synthesis is another approach that we do, where you pelletize all the raw meal plus a fuel, that's a lignin or a biomass-based fuel. So that's all the temperature that you give to the material, 400 degrees Celsius. The internal reaction kicks up and goes to calcining temperatures, goes to 1000 degrees or so, which means you see the pellet getting heated up, and finally burning inside completely. All these points are all heat burning inside, you calcine it. So, by just giving 400 degrees Celsius temperature, you can get to about 1000 degrees inside the pellet, which means your external heat delivery needs to be lower, which means your carbon emission is lower. If you use calcium hydroxide that comes from electrolysis in this process, it becomes again an effectively very low carbon process. Okay, and finally, to electrochemical technologies, I kept it for the last because these are the low technology readiness level strategies as of now. Quite a bit of challenges in scaling up. But there are three basic methodologies. One is aqueous electrolysis using water. The other is high temperature electrolysis up to about 400, 500 degrees Celsius using molten carbonates. You can have lots of different molten carbonates, sodium carbonate, magnesium carbonate, combination of sodium, magnesium carbonate, lithium carbonate, lots of different molten salts in which you can use limestone to lime conversion and get solid carbon as an output instead of CO2. Your solid carbon will be deposited in the electrodes. And the last one is seawater electrolysis. Again, I'll show you some examples where you can actually extract calcium and magnesium from seawater to and then enhance the ocean's capacity to absorb CO2 because you are taking CO2 from the ocean to create calcium carbonate and magnesium carbonate. And those calcium carbonate and magnesium carbonate can be raw materials for cement manufacturing so that you don't have to extract new limestones from the earth. It's a renewable ocean cycle. But remember, all electrolysis method create lime or calcium hydroxide. They don't create cement. The cement, you still have to do a process to merge lime and silica. Right. So overall concept, you have for water electrolysis, you have a decarbonation cell, where you have limestone that goes in water. It creates hydrogen in this process. It creates water is split into oxygen and hydrogen. Oxygen is mixed with carbon dioxide that gets out. That carbon dioxide goes into liquid fuels, all of the other technologies, CCUS, end of use storage, all of that, or even for oxy-fuel to fuel the kiln. And then the calcium hydroxide comes in as a raw material. Remember, the CO2 has gone away and you've used or stored the CO2, so there are no emissions here. Calcium hydroxide come in, aluminosilicates come in, some of these oxy-fuel can go in, and that's the fuel for it, and you get cement. Again, this heat, you can do renewable heat from all these renewables. So again, effectively a very low carbon process. It's not net negative carbon, but a low carbon, effectively a very low carbon process. That's how all the electrochemical technologies are structured. Now the cell is different, where the CO2 goes is different, where you get the CO2 and store it is different, how you heat this is different. All of those will be different, but this is the basic concept of how all electrochemical technologies work. There are electrochemical technologies where you can co-produce carbon negative supplemented cementing materials and clean fuels, especially when you use demolition and mine waste as raw materials into the cell. Calcium bearing silicates can be converted to calcium carbonate. There were companies who were actually doing it. Now some of them are out of business. Some of them still are surviving because the market is not that huge, because the technologies are still not very mature. Captured CO2 can transform into dissolved bicarbonates that can go into ocean to mitigate ocean acidification. If you remember, if you listen to what is happening with the ocean, with lots of CO2 going in the ocean cycle, ocean acidification is happening. Captured CO2 can be transformed into bicarbonates, and this is a very highly alkaline material to mitigate ocean acidification. Water electrolysis will generate hydrogen and oxygen as green energy carriers or for oxy-fuel. So again, electrolysis gives you a lot of different options. The problem with electrolysis is that how do you scale it? Challenges with electrodes, challenges with electrolytes, challenges with membranes that you have to completely recycle and renew. But again, these are technologies and challenges that people are really working hard to do it. Calcium hydroxide from calcium carbonate, a simple electrochemical cell. Again, you can even teach this to an undergraduate um, civil engineering class because it's very, very basic chemistry. There is water electrolysis, H plus plus OH minus. This electrode splits water to H plus and oxygen and electrons, and then you have limestone that is split into carbonate ions and calcium ions. Calcium ions get combined with this electron, this hydroxides to form calcium hydroxide in this electrode. Again, to balance it, the excess hydroxides mix or water splits into oxygen and hydrogen. The hydrogen is released here, carbon dioxide plus oxygen is released here. This is oxy-fuel combustion facility, or you can store it and take it somewhere else for other purposes. So very simple electrochemical cell, but again, challenges with how would the electrodes work, How would the exchange, ion exchange between these membranes work? How quickly you have to replace those membranes? What is the clogging potential? What happens with the alkalinity that is produced in the system? How would you separate carbon dioxide and oxygen? So all of these things are big challenges, but from a very fundamental chemistry point of view, you can introduce this to even an undergraduate class. Zero Cal is another new technology that has come up where they're using seawater mediated electrolysis to produce calcium hydroxide. Same idea, ambient sub-boiling temperature process. So you have limestone coming in to an electrochemical cell, calcium carbonate, water splitting, hydrogen goes out. That'll be the energy source. Calcium carbonate becomes calcium hydroxide. The CO2 is immobilized as bicarbonates. You take it to the ocean as calcium bicarbonates to replace ocean alkalinity. Calcium hydroxide goes into cement manufacturing and then combines with silica and alumina. So again, instead of limestone coming here directly, you're getting calcium hydroxide coming here through one more sub process. Now, lots of water needed for this process. Again, what lots of water can be recirculated and recycled, but it'll require quite a lot of water. You need chelating agents to couple them with calcium. You need different types of electrodes, and that's what I talk about, the scaling potential. But very promising, probably doable. You can also tweak this technology ever so slightly to do seawater mineralization. Same idea, cathodic chamber electrolysis produces hydrogen, anodic chamber acidified seawater because you've taken all the alkalis out of it, and then calcium magnesium depleted seawater will go into a solids handling catalyte processing process. You will get calcium carbonate and magnesium hydroxide, and then you can use it in whichever way you want. You can use calcium carbonate to get calcium hydroxide, or you can use calcium carbonate as it is, and then anolyte realkalinization with some ground silicate. So again, you can filter out the calcium carbonate. You can take the carbonate-rich catholyte back to the ocean and capture more CO2 because now the ocean can take more CO2. So this is also another process, a little more complicated. You have to locate this facility right next to the ocean. You need to have some ways in which you transport materials to wherever the silica sources are available for cement production. But those are challenges that are again, like I said, 5-10 years down the line, more of forward-looking challenges. Like I said, need to replace cost and carbon intensive electrodes, electrolytes, all of them. Engineering optimization is lacking. How do we deal with impurities in limestone? Gas capture separation process is expensive. Sometimes the augmentation required for gas separation is more expensive than a typical um, pyroprocessing facility. So that's another challenge in scale up and operation, but there are ongoing research challenges. So in summary, again, cement is a very hard to abate sector. You have to look at unconventional approaches. We know what conventional technologies will do. We know that if we don't control the process emissions, if you don't control that 50% emissions from limestone calcination, we can't go too far. What we need for this are new technologies. There are short-term levers, clinker reduction, design efficiency, manufacturing energy efficiency, all that. But long-term levers are what we talked about in detail: electrification, electrochemical processes. This will require lots of reimagining, lots of rethinking. Zero carbon process not enough by itself. We need to become net carbon negative. We need new scientific and policy strategies. We need a global market with differing specifications and all of that before we get to real implementation of these technologies. But again, research is happening in these directions. Some of them are real fundamental science. Scaling challenges are there. But again, with lots of R&D happening in all parts of the world, and everybody getting the seriousness of this, we hope that in the next 10 years, we will be able to get significant advances in the manufacturing of cement, to get lots of manufacturing efficiency, lots of carbon efficiency, and eventually make sure that we have a very good sustainable construction ecosystem. Thank you very much. I want to thank all the students who are working on these projects, my collaborators on different projects, and all the funding agencies that have funded our work on decarbonization of cement. Thank you very much, and I'll be happy to take questions if you have.
Thank you very much, Professor Narayanan, taking us to the wonderful world of futuristic of the cement production. Of course, with the current cement production, there are some sustainability challenges. But of course, I can see that yes, there are areas of research where we need to step in. And there are, whenever I research, we say whenever there are challenges, opportunity lies along with them. So thank you for taking us for 1 hour to the wonderful world of future of cement production. So I can take one or two. I think Dr. A.K. Singh is here. So he's from Hypertech Cement. So Singh Saab, if you want to say something.
Yes, sir. Sir, good afternoon. Good afternoon to you and the NCB team for the organizing such very useful the webinar. And so, sir, we are thankful to Professor Yan Narayanan for the nice presentation and you know that now the carbon dioxide. Yeah. So we all are aware about the impact of that. You know, the carbon dioxide and cement sector, whose contribution is more than the 6-7%. And initially, what he explained that the cementitious material or even the carbon capturing that we are learning. But the professor, we have come across that the new technology, what he explained, that is very, very eye-opening. So that particularly he talked about the renewable electrification and process of the heat, and he suggested that separate modularization of the calcination and then that clinkerization in the kiln and the starter of that kiln. That really that will be a great helpful to the industry for the reduction of that, you know, the CO2 emission, not only the CO2 emission, but the overall, I think that will scale up the production and the new technology, what we were not aware about that, very, very, the recent, what he talked about the electrochemical technologies. And that will be really that very fantastic what he explained. So now we can say the future of that. Sometimes at many platforms, what will happen to the cement industry if the that natural resources of the limestone that will be exhausted. So we know that in the current scenario there is no material which can challenge the limestone as far as the cement manufacturing looking into the scale up and all. So this technology, I think that will be a option of that limestone, the natural reserve of that, and conversion of the electrochemical technology zero cal. What he explained that the calcium carbonate in place of the putting in the kiln that to transform in the calcium hydroxide, and that obviously that will be solution of the reduction, total reduction of, you can say, the net zero of that. So really the fantastic presentation there. A lot of the new things we could learn, and hopeful that in coming days, such kind of the research that the what is happening, that will provide a very good option before the cement industry. Thank you, sir.
Thank you. Thank you so much. Thank you. I think Dr. Singh is muted.
So thank you, Dr. A.K. Singh. Manish Karandikar sir is also there. If he is sir, forward for your comments.
Yeah. So thank you, Professor Narayan, for this excellent, giving us excellent insight into the different avenues of CO2 reduction technologies. I mean, these are some of the technologies what you have presented again are basically the futuristic, and I think more and more research has to go in so that finally this will get the lab skill should come to the commercialization. That is one. I think I have two questions to Professor. One is, you have mentioned about the electrification technology for, calcination, etc. So, I mean, as a concept, yes, but whether it has been piloted, that is my point number one. Second, what is your opinion on the microwave heating? Because a lot of work also has gone into the microwave heating of the raw material. That is one. Second point, I think, please enlighten us on the geopolymeric binders, because I think last more than 20 years, we are hearing a lot of research has gone inside the geopolymeric binder. But my question here is why it is not picking up globally, whether it has something to do with the uh, modal provisions, or there is really a scaling issue in terms of the raw material availability.
Wonderful. Thank you very much. Let me talk about first the piloting of electrification technology. So there is a technology called Lilac. Europe, they have piloted electrified kilns for calcination. You cannot do. They have not gotten up to 1500 degrees Celsius to clinkerize it, but they have enough temperatures, 1000 degrees Celsius to calcine. So electrification for calciners are already there. Pilot technologies are there. Microwave heating is a very good technology. There are works that is going in the volumetric microwave heating ideas. There are a couple of companies who have some very basic microwave reactors for cement. There is something called in microwaves. There's something called a thermal runaway. You are not able to control temperatures because when you have lots of these particles, these micro scale particles, in a typical calciner, you have heat transfer through conduction. There's lots of heat loss when you have conduction. All in volumetric heating, you're not able to control that, and there is something called the thermal runaway. So you end up wanting 1500, you end up getting 3000 in the whole thing, and you get a completely different set of melt which you don't want. And they have not been able to really control that process with a large scale microwave heat. Whereas in lab scale, they have gotten wonderful results with microwave. But I think they're looking at controlling these processes, getting the right power and right frequency to control this process. So I think that will come at some point of time. With respect to geopolymeric, yeah, is there something else?
No, please continue.
With respect to geopolymeric binders, in the US, so in early 2010s, 2010, 2012, I was advising about 4 different companies who were doing geopolymers. One company was doing exclusively geopolymeric binders for very high temperature applications like rocket launches and spacecraft launches, because the base will get extremely hot, things like that. So, and one company was purely doing for refractories, and there are a couple of other companies trying to do in concrete. All of them have gone bankrupt. All of them have gone out of business in the last whatever 10 years. There's really there are a few companies here and there doing small things, but there's really no company doing geopolymeric concrete in the US. Australia does it very well. Europe in patches does it very well. India, I think, is doing reasonably well. In the US, for some reason, geopolymers were never able. My explanation partly for it is that fly ashes have become very expensive in the US. So if you want to use fly ash as a geopolymeric material, fly ash, add to that the cost of sodium hydroxide or sodium silicate or potassium hydroxide or potassium silicate, add to that the need to control this, add to that the need to make sure that the people who work with this take the proper safety precautions dealing with these high alkalis. All of that has resulted in geopolymeric concretes becoming very, very, very expensive. Slag, we don't have slag at all in the US. All the slag is accounted for. There is no extra slag lying around everywhere. There are a few waste materials. So I did a project with a very large mining company called Freeport McMoran, using all their mining waste to geopolymerize. And we actually did it. We gave them a few formulations. Now it's up to the mining company to invest money to put in a geopolymeric plant. They did a market analysis. If they want to sell geopolymeric precast concretes in lieu of typical OPC precast concretes, they came back and told me that the price is going to be 2 times. They have to sell the concrete at twice the price. Who is going to buy concrete at twice the price? So lots of these market forces has resulted. It's nothing to do with the quality of the material, nothing to do with the science and technology of that. It is purely market driven that this is not taking off in the US.
Okay. Thank you. Thank you very much.
So, thank you, Manishi and Narayanji. So there are some questions in chat box. My colleague, Dr. Varsha, she will take those questions. So quickly, can you take up those questions so that then we basically.
There are a few questions in the chat boxes, as Professor Narayan can also see. I'll just read it out. Can you cite an example of new alternative SCMs?
Okay, there is a company called there's a company called Terra CO2. You can go and Google it. This is a new tech company that got about $85 million by investors. They raised $85 million from investors. They're actually making a new SCM, a low carbon SCM. It's not a zero carbon SCM, but from silicate rocks. So that is one. There is a company called Carbicrete, which carbonates slag to form either a binder directly or an SCM. There are low grade fly ashes that you can never use, which have very high amounts of sulfates. For example, fluidized bed ash fly ashes and things like that. People are using that and using chemical beneficiation of those ashes to make an ASTM C618 type SCM. So you have a huge family of SCMs. Even the definition of what an SCM is getting broader and broader by the day. If you look at it, and lots of people are coming up with lots of them, and I just gave you 3 examples, and I can give you 10 more if there is time.
The above question was from Dilip Makina from JSW. The next question is from Mr. Shashank Malan. Can alternative fuels also be used with these technology of heating?
Can alternate fuels also use with these technology of heating?
Yeah, I think even that the heating technology which you mentioned in your presentation, can that be used for alternate fuels also?
Yes.
I think that's what.
Yeah. So when you say alternate fuels, what I was talking about is coal, for example, being replaced by natural gas. Right, coal being replaced by burning of waste materials, all of that, right? So yes, you can do some of that and then if you look at even the extension, I don't want to even stop at alternate fuels, right? We want to use totally renewable energies. Alternate fuels are not carbon efficient also. There is carbon impact in alternate fuels as well. So I want to get to a point where we can use completely renewable solar and wind and hydroelectric, and those things can be beneficially used for high temperature production. The only point there is there has to be an intermediary step. Even if I can get solar to get to 1500 degrees Celsius, I need some heat storage mechanism. I can't directly use, right? And solar is not available in the night. So basically, I don't have continuous heat availability. How do I store heat and use that heat? And that's where heat storage technologies also come in. So some of these alternate fuels will require augmentation with heat storage, if that answers it.
Right. So the next question is from Mr. Sriram Pradeep, who wants to know that early age carbonation curing of concrete primarily affects the surface, while the core remains largely uncarbonated. What are your thoughts on this phenomenon?
Well, this is a long answer. In reality, it depends on when you start carbonating, right? And pretty much in every carbonation curing of concrete, you will be doing a great disservice to concrete if carbonation impedes hydration. Hydration is your basic strength provider, right? So you want some carbonation to happen, and then you want the hydration to happen. So if it's in the fresh state, and if you inject CO2 into the chamber that it is hydrating in the fresh state with a little bit of temperature, maybe 50 degrees Celsius, what happens is you will have lots of diffusion of CO2 into the system, and you will have quite a bit of carbonation, calcium carbonate crystals happening very early on. And that is how some of these early carbonation curing is happening. The surface control only happens on the surface is when you're curing it at much later ages, when the structure has densified and diffusion is taking much longer time. So it's a careful interplay. Precast companies do it very well. I know precast companies that actually do carbonation curing, where they use quite a bit of carbonation at slightly elevated temperatures to get your lot of early age properties, and then they cure it later, let hydration take place or pozzolanic reaction take place later. So it's again tweaking of the process and control of how quickly you can do this.
So the next question is from Mr. Satyen Kumar from Prism Johnson Limited. He has a couple of questions. The first one is why Portland limestone cement is not manufactured in India, but for the benefit of the audience, this PLC, the code is already being prepared, and it's at BIS, and hopefully it will be coming out in the next few months. And the next question is why MgO content is limited to 6%, even when the clinkerization technology is much more advanced, which enables presence of very less periclase. Can we increase MgO content in clinker?
That's a very complex chemistry question. I have seen MgO in certain clinkers, higher MgO content in certain clinkers, and they don't cause noticeable autoclave expansion. I have seen much lower than the ASTM specified limits of MgO, and still that concrete expanding, right? So it's an interplay of different things, interplay of how you process the materials. And I think the quality control person in a cement plant who does this is probably a chemist is much more qualified to answer this question than I can, because it is lots of material interplay happens. You're putting in a lot of materials. These are not phase pure materials. None of what you make are phase pure materials that they use in electronics industry or any of those advanced industries, right? We are dealing with what we get. And therefore, lots of interactions. Even the idea of iron, right? We look at C4AF as something that just forms in the melt and helps all of those. But really, the phases of how iron is integrated in influences hydration to quite an extent. But have you seen Fe in any of the hydration reactions? You don't see them, right? But they do influence hydration reactions. Its impact with alkalis and all of those. So it is, and also the calcium magnesium cationic size difference. And there is, if you start to look at closely at how some of these hydration reactions happen and some of these lattice structures form, the calcium to magnesium size difference of these cations and the surface charge of these cations simply cause lattice expansions beyond what is required. Sometimes only very small amount is needed. Sometimes large expansions don't happen even with large amounts. So it's more of a chemistry question, which I'm not an expert in that.
So the next question is from Mr. Prateek Sharma, who wants to know that in plasma-based electrification, which type of plasma arc, transferred or non-transferred, is being used in setups? What is the plasma torch capacity?
So what we do in a lab, in a lab scale test setup to make about 20 pounds of cement in about a couple of hours is argon. We use argon because in the lab, argon is the one that's easily controllable. CO2 plasma requires an extremely large arc, plus argon and all those inert gases, you can use very small arcs so you can control in a lab-based situation. But CO2 plasma can be used in a large-scale setup. There is US military uses CO2 plasma to burn lots of their waste materials that they can't throw anywhere else, right? So there's already CO2 plasma arcs that are being used. But nitrogen and argon are better in terms of controllability. A plasma arc that you need in a cement plant probably would be a megawatt or half a megawatt plasma arc. It will be very, very, very power consuming. And that's why you want So we have 50 kilowatt plasma arcs in small scale pilot plants. But if you want to get to 100, 200, 500 kilowatt arcs, it becomes extremely complex. And that's one limitation with plasma technology as of now, how to power those arcs.
You can take one more question then, because there is a queue of questions. So what we will do, we will share your email ID so they can directly get in touch.
Yes, I'm okay with that.
So there's one last question, if you can, sir, from Pradeep, Mr. Pradeep Kumar Reddy. Are there any technologies to reduce the heat required for calculation process and capture CO2 at lower cost?
So the key question is lower cost. Are there technologies? Yes. We can reduce the heat required for calcination. We can do effective heat transfer processes. You can do pelletization of the fuel, raw meal mix. You can do several different things to reduce the heat. The question is, they all add to cost. And the cost is large because we are typically looking at things at smaller scale and trying to understand it. But I think when you scale up, there is definitely a reason for a lower cost, a much more efficient system. So, you have, for example, one of the technologies that we are very seriously evaluating is injection of steam in calcination, steam assisted calcination, for example. Right? Can you throw in steam into the calcining chamber? We have theoretically thermodynamic calculations show that easily there is 150 degrees Celsius reduction that you can get for limestone to convert to lime thermodynamically. Now, none of those systems are thermodynamically efficient to that level. So when you start to manufacture those systems, heat efficiency, we have seen 75 to 100 degrees Celsius reduction in a smaller scale setup. In a larger scale setup, I really don't know if we'll get better or we'll get worse. But whatever it is, if you assume that we can get 75 to 100 degrees Celsius reduction, any drop from 950 to 850 is phenomenal, because your CO2 use or your fuel enthalpy as you go higher and higher temperatures will start to drive up the emission capacity as well. So 100 degrees Celsius for steam assisted calcination, good enough. Now, what's the problem with steam? How to do the flue gas that comes out of it. Now you're getting a flue gas that is rich in moisture. And if you're using CO2, if you're getting a hot CO2 that is combined with moisture, you're not using that CO2 efficiently. That's not a good CO2, right? Then you need to have separation. CO2 moisture separation is an extremely difficult and complex process. So now, do you want that? If I'm just venting out into the atmosphere, it's okay. But our whole idea is not to vent it out in the atmosphere. So now your calcination efficiency gets higher, but your associated cost of purifying and separating the gases becomes more expensive. And that combination, that combined effects is where this entire technology, this entire field is having trouble, because this is like a patient really sick. You give him one medicine, there is a side effect, something else is happening. You don't know if whatever is happening as a side effect is dangerous or better. And that is where we are all stuck with.
Thank you very much, sir. I think there are a couple of more questions. The questions are coming on, but I think we have shared sir's mail ID. So those who are interested may kindly contact sir through his ID, and let's wind up this session. And so it is my pleasure to propose a vote of thanks on the occasion of National Science Day 2025 celebration at NCD. Firstly, I feel glad to thank our Director General, Dr. L.P. Singh, for this noble idea of launching NCD Distinguished Lecture Series on the occasion of National Science Day celebration, and inaugurating the same with a remarkable first lecture, which we have now heard. We are grateful for your immense commitment, sir, and timely and right steering of organization in the path of research and innovation. Next, I would like, it gives me immense pleasure to thank today's esteemed speaker, Professor Narayanan. So in spite of several commitments and a very busy schedule, he has enlightened the listeners with the most trending and extremely crucial topic of coupling efficiency of materials with manufacturing process and decarbonization. There is no doubt that the talk has kindled the minds of all the people who have attended the session. And the question answer session is an example of that. So we express our heartfelt gratitude for accepting our invitation and gracing this occasion today. I'm extremely thankful to the various service centers, especially the IT department, for the flawless arrangement which was done throughout this session. A special thanks to all the participants for joining in such a large number and enthusiastically participating in the question answer session and making this program a grand success today. Wishing all of you a very happy Science Day. Have a great scientific year ahead. Thank you.
Thank you, Professor Narayanan. It was more than 200 online participants were there that I could see. Apart from that, our colleagues were sitting together in groups at various centers. So I can see a big participation, and this is a good start for our NCP distinguished lecture series on Science Day. And I hope in future also we will get other kind of supports also. Means so many projects we are doing, and we would like to collaborate. NCP would like to collaborate with you on many of these topics, which are of mutual interest of both Indian cement industry as well as for the
Absolutely.
US.
Absolutely, my pleasure.
Thank you very much. Thank you very much for accepting our invitation, and we will be getting in touch with you for future collaborations. Thank you.
Thank you so much. Thank you so much for the invitation, and thank you very much.
Thank you everyone for your participation.
Thanks.